Hello everyone, welcome back to Math 251. We've been talking a lot about how to graph functions and what various aspects of the graph are, such as concavity, inflection points, increasing, decreasing, all of that. So today we are going to use all of that information in order to graph some equations. Our mathematician of the day is Maria Agnesi, who was an 18th century mathematician who wrote a math textbook to explain math to her 20 younger siblings. She was the first woman to be appointed to a professor position at a university. That's pretty dedicated, guys. Like, I think I helped my sister with her homework, but I would not consider writing a math textbook to explain it to her. And our math history fact of the day is a theorem produced in 1742. The theorem says that every even number greater than 2 is the sum of two prime numbers, has still not been proven. This theorem is called a millennium problem. I think Yale or Harvard funds these problems. Basically, if you create a good enough proof of this problem and you prove that it's true, then you get $1 million. So if you're ever bored, maybe just try this proof and who knows, maybe you'll end up with $1 million. All right, so yes, we are talking today about how to graph functions. So how do we use all of the information that we can collect from a function in order to graph it? So my first step is I need to identify the domain. Is it defined everywhere? Does it have any asymptotes? Does it have any holes? I need to first identify the domain. Next, I find the symmetry . If our function is a polynomial and all of the terms have odd powers, then it's called an odd function, which means that it's symmetric about the origin. That means that if you flip the function over the y-axis and then over the x-axis, you will get the original function. Or if all of the terms are even, then that means it is symmetric about the y-axis. After we find the symmetry, we need to compute f and f prime, because those can tell us a lot of things. Oh, sorry, f prime and f double prime. F prime and f double prime. And then we'll use f prime and f double prime to find the critical points and possible inflection points. And remember, our critical points is where f prime of x equals 0, or f prime of x is undefined. And then our possible inflection points is where f double prime is equal to 0. So we set f prime and f double prime equal to 0 and see if there's anywhere that f prime is undefined. Using this information, I find the intervals of increasing and decreasing. Using the number line that we've been doing, and concavity. We want to find those two things. Next, I can find the extremum and the inflection points. Remember, our inflection points is where my graph changes concavity. Finally, well, not finally, but next I locate the asymptotes and determined end behavior. So vertical and horizontal asymptotes, and determine end behavior. Then I need to find my x and y intercepts. And that is my last step before I graph. So yeah, there are a lot of steps here. That's because a graph has a lot of information, right? Inflection points, concavity, asymptotes. We are finding all of this information from our equation. So it's a lot of steps, but we'll go through a couple of examples and hopefully this will make more sense. So we want to use these guidelines to graph the function f of x is equal to 1/3 x cubed minus 400x on its domain. So my first step is I need to identify the domain. In this case, we have a polynomial. So our domain is -infinity to +infinity. Since it's a polynomial. All right, my next step is I need to find the symmetry. Is it odd or even or neither? Well, in this case, both of our terms, x cubed and x to the invisible power of 1, those are both odd numbers, so this is an odd function, which means that I am symmetric about the origin. That will help us graph. Now I need to compute f prime and f double prime. So in this case, we have a polynomial, so it's pretty straightforward. I see that f prime of x is equal to, let's see, 1/3 times 3 is just 1, and then I have x squared minus 400. That's f prime. And f double prime of x, then, is equal to 2x. My next step is I need to find the critical points and the possible inflection points. So I find my critical points by setting f prime equal to 0. In this case, f prime is a polynomial, so it's defined everywhere. So f prime of x is equal to x squared minus 400, and I want to set this equal to 0. If I add 400 to both sides, I get x squared equals 400. And taking the square root of both sides gives me x equals plus or minus 20. So these are my critical points. And what about my possible points of inflection? Well, that is setting the second derivative equal to 0. And obviously, if 2x equals 0, this means that x is equal to 0. So this is our possible inflection point. All right, that was step 4. In step 5, I'm going to use my critical points and my possible inflection points to find the intervals of increasing, decreasing, and concavity. So I need to draw my number line here. First, I'll do f prime. So I need to plot my two critical points. In this case, I have -20 and +20. I'm dealing with f prime. So I need to pick a point in all of these intervals. So I'm going to pick 0 and 30 and negative 30. So I need to plug negative 30, 0, and 30 into f prime to see whether or not it is positive or negative. Remember, if f prime is positive, that means I'm increasing, and if f prime is negative, that means that I'm decreasing. So let's see, if I plug in negative 30 into f prime, oops, I don't know what just happened. I get f prime of negative 30 is negative 30 squared minus 400. Negative 30 squared is 900 minus 400, so this is positive 500. The number doesn't matter, but I get that in this interval right here, I am positive. Okay, f prime of 0 is equal to 0 squared minus 400, which is negative 400. So in this interval right here, I'm negative. And then we'll do f prime of 30. We don't actually have to do f prime of 30. I will, but we can employ our symmetry here. So because it is symmetric about the origin, I know that it has to be positive on this interval because of the symmetry. So if I went through this, I would get a positive number. You can check me on that. But I know due to the symmetry that this region has to be positive. So what does this tell me about increasing and decreasing? Well, I see that I am increasing from negative infinity to negative 20 and 20 to infinity. And I'm decreasing from negative 20 to 20. That's what this number line tells me. Next, I need to find concavity. So I need to do this same number line thing with f double prime. So I will plot my only possible inflection point, 0. And if I pick a number on either side, I'll pick negative 1 and positive 1. I'll need to plug both of these into f double prime to find concavity. So f double prime of negative 1 is equal to negative 2 times 1, which is negative. So over here I am negative. That means that I am concave down. And if I take f double prime of positive 1, I get that this is 2 times 1, which is positive. I'm sorry, when I took f double prime of negative 1, that should be positive 2 times negative 1. Still negative, but. Okay, so this is positive. So this tells me that I'm concave down from negative infinity to 0 and concave up from 0 to infinity. So concave down from negative infinity to 0 and concave up from 0 to infinity. What does that mean about 0? It does mean that since I'm changing concavity here, this is an inflection point. Okay, so now we found our intervals of increasing, decreasing, and concavity. So my next step, 6, is to find the extremum and inflection points. Well, I know my inflection point is 0. So I need to find my local max and my local min. So if you remember from last lesson, we learned the first derivative test. And the first derivative test says that if I look at this f prime right here, and I am changing from increasing to decreasing, then I have a local max here. And according to my first derivative test, if I'm changing from decreasing to increasing, I have a local min here. So I have a local max at x equals negative 20. And if I were to plug in negative 20 into my original function, 1/3 x cubed minus 400x, I would get a y value of 5,333 and 1/3. And I have a local min at x equals positive 20. And again, if I plug this into my function, I would get 5,333 and 1/3. Oh, negative, sorry, negative. And we know that we have an inflection point at x equals 0. And if I plug in 0 into our original function f, I get y equals 0 there. Okay, step 7, locating asymptotes and determine end behavior. I don't have any asymptotes, neither vertical nor horizontal. So no asymptotes. What about my end behavior? So my leading term here is a 1/3 x cubed, and my end behavior is determined by my leading term. So what does x cubed look like? It looks like this. So that is what my end behavior will look like. As x goes towards negative infinity, f of x goes towards negative infinity. And as x goes towards positive infinity, f of x also goes towards positive infinity. Okay, last step before we graph, finding our x and y intercepts. So we have one of them here, right? This is our y-intercept. Y-intercept at 0, 0. And what about our, and that's also obviously one of our x-intercepts. But to find my x-intercepts, I need to set my function equal to 0 to see where else I have an x-intercept. So x-intercept, I set my function 1/3 x cubed minus 400x. I set this equal to 0 since I want the y value to be equal to 0. If I were to factor out an x here, I would be left with 1/3 x squared minus 400 equals 0. So if I set x equal to 0, that gives me x equals 0, which is already accounted for here. And if I set 1/3 x squared minus 400 equal to 0, I get 1/3 x squared equals 400. If I were to multiply both sides by 3 to get rid of that 1/3, I'd get x squared is equal to 1200, which means that x is equal to plus or minus square root of 1200, which is 34.6. So these are my x-intercepts. All right, are you guys ready for the big reveal? Now we can finally graph our function. It's pretty amazing that we can put so many details into this graph, even though we just have the equation. All right, so let's graph our intercepts first. That will kind of give us a good idea. So I have a y-intercept at 0, 0, and an x-intercept. And then I have an x-intercept here at 34.6, and here at negative 34.6. Those are my intercepts. What about my max and min? I have a local max at x equals negative 20. So maybe somewhere right here. So this is the point negative 20, 5,333 and 1/3. Obviously this is not to scale, but that's all right. And then I have another local min right here. This is the point 20, negative 5,333 and 1/3. Okay, I have a few points here. My end behavior, I know that this, as x goes towards negative infinity, so does f of x. And as x goes towards positive infinity, so does f of x. And I know that I am, let's go towards to increasing and decreasing now. So I'm increasing from negative infinity to 20. So I know that I'm increasing here. I'm decreasing from negative 20 to positive 20. And I pretend that goes through the origin. And I'm increasing again from 20 to infinity. So this is my function. So let's go through and check real quick to make sure we have everything. So our domain is negative infinity to positive infinity. That's good. It is symmetric about the origin. That means if I flip this function over the x-axis and then the y-axis, we would get the same function. So we're good there. We have a local max and a local min at negative 20 and positive 20. So those are the critical points. If I were to draw tangent lines at those points, they would be horizontal. What about concavity? Well, I see that I am concave down because I look like an upside down U from negative infinity to 0, and I'm concave up from 0 to infinity since it looks like a right side up U. Yeah, so I think that's everything. I know this is a lot of information and a lot of different details to go through, but it is pretty remarkable that we can find so much out about our graph just by using calculus. So good job, guys. Give yourselves a pat on the back. Okay, let's do another example. We want to use these graphing guidelines to graph f of x equals 10x cubed divided by x squared minus 1 on its domain. So our first step here is to figure out what the domain is. In this case, we don't have a polynomial. We have a rational function. And the domain for a rational function is anywhere that the denominator is not equal to 0. So for the domain, our denominator cannot equal 0. Our denominator here is x squared minus 1. So that equals 0 whenever x equals 1 or when x equals negative 1. So our domain is negative infinity to negative 1, union negative 1 to 0, to positive 1, union 1 to infinity. We are excluding the points negative 1 and positive 1, since they make our denominator equal to 0. What about, so number 2, this is trying to determine the symmetry. So when I have a rational function like this, I can determine the symmetry by looking at the leading term on the top and dividing it by the leading term on the bottom. So on the top I have a 10x cubed, that's my leading term, and I can divide that by x squared. What does this equal? Well, this is equal to 10x. And this has odd symmetry. That means that our function f of x also has odd symmetry. So we are symmetric about the origin, just like the previous example. All right, that's our symmetry. In step 3, we need to find f prime and f double prime. So let's do that. To find f prime, I'm going to have to use the quotient rule. Since I have a quotient of 2 functions. So that makes f prime equal to the bottom times the derivative of the top, that is 30x squared, minus the top times the derivative of the bottom. All of this over the bottom squared. And since I am going to be setting f prime equal to 0 eventually, I do want to get it as simplified and factored as possible. So if I were to expand this out, I would get 30 x to the power of 4 minus 30x squared minus 20x cubed. All of this over x squared minus 1 squared. And what can I factor out of each one of these? Whoops, that should be 20x to the power of 4, shouldn't it? Sorry about that. Okay, so clearly this 30x to the power of 4 and 20x to the power of 4, I can combine those. So this will be equal to, if I combine 30x to the power of 4 minus 20x to the power of 4, I get 10x to the power of 4 minus 30x squared over x squared minus 1 squared. And now what can I factor out of each of these terms? Well, each of them is divisible by 10 and x squared. So this will be 10x squared times x squared minus 3 over x squared minus 1 squared. So that is f prime. Woohoo! So fun. All right, and next I want to find f double prime. And again, I'm going to have to use the quotient rule. When I find f double prime, I'm going to find the derivative of this function right here. I mean, these two are the same, obviously. But I'm going to use this unsimplified version to find the derivative. That way I don't have to use the product rule on this one right here. So I'm going to have to use the quotient rule. So f double prime is equal to the bottom, x squared minus 1 squared. You know what? I'm going to scoot over. I'm going to run out of room. Okay, f double prime is equal to the bottom times the derivative of the top. That is 40x cubed minus 60x minus the top. I'm running out of room. Times the derivative of the bottom. To find the derivative of the bottom, we will have to use the chain rule. And that will be, using the chain rule gives me 2x times x squared minus 1. I don't know. Sorry, I'm running out of room. All right, so we have 10x to the power of 4 minus 30x squared times 2x x squared minus 1. All right, that is the top. All of this divided by the bottom squared. X squared minus 1 squared, which would be to the power of 4. Okay, I am going to spare you the details here. If you don't believe me, you can work it out yourself. But this is just a lot of algebra, and I don't want to bore you with that. So if I simplify this, I will get 20x times x squared plus 3. All of this over x squared minus 1 cubed. One of our x squared minus 1's cancel. If you're curious about the algebra, I can work it out on the Zoom session for sure. All right, so now I have f prime and f double prime. Very exciting. Next, in my fourth step, I need to find my critical points and my possible inflection points. So I need to set f prime equal to 0 and see where it's undefined. So f prime of x, let's see where it's undefined first. So here I do have a rational function. I need to be careful about whether it's undefined anywhere. And it is undefined at x equals positive 1 and x equals negative 1, because that's what makes the denominator of f prime equal to 0. So this d and e at x equals plus or minus 1. These are two critical points. And what about when it is equal to 0? So when a rational function is equal to 0, that means I set the top equal to 0. So I have 10x squared times x squared minus 3 equals 0. So I set each of these terms equal to 0. If I set 10x squared equal to 0, I get x equals 0. And if I set x squared minus 3 equal to 0, I get x is equal to plus or minus square root of 3. So here I have a lot of critical points. I have critical points x plus or minus 1, x equals 0, and x equals plus or minus square root of 3. These are my critical points. And I need to find my possible inflection points by setting my second derivative equal to 0 and seeing where it is undefined. So I have f double prime of x. First of all, where is this undefined? Well, it is undefined at x equals plus or minus 1 again. And where does f double prime of x equals 0? Well, again, I set the top equal to 0, so I get 20x times x squared plus 3 equals 0. X squared plus 3 never equals 0. It just doesn't. So all I have is 20x equals 0, which means that x equals 0. So I have 3 possible inflection points. This is a pretty exciting graph, guys, huh? All right. Next, we need to find where I have local maxes or local mins. Oh, sorry, actually 5 is finding the critical points. So I need to draw my number line here. I have a lot of different things going on. So I'm graphing f prime, and I'm graphing my possible critical points. Or my critical points, I don't have possible ones. So I have 0, plus or minus 1, and plus or minus square root of 3. Very exciting. So I need to pick a term or a number from each one of these little intervals. So I am, however, going to exploit this symmetry because I do have odd symmetry. So that means that, anyway, we'll talk about that once we get there. So I'm just going to work on the left side of 0. So I'm going to pick -1/2. What's between -1 and square root of 3? I'll pick -1.5 and -2. Okay, so if I take f prime of -2, this is 10 times -2 squared. That's positive. -2 squared minus 3, that's also positive, over -2 squared minus 1 squared. That is positive. So I have positive times positive divided by positive. So I'm positive here. Positive, that means I am increasing on that interval. It also means, because of symmetry, that I'm increasing on this interval because I'm symmetric about the origin. I am allowed to exploit symmetry like that. Okay, let's look at f prime of -1.5. F prime of -1.5 is equal to 10 times -1.5 squared, that's positive. 1.5 squared minus 3, that's negative. So I have positive times negative, which is negative, over 1.5 squared minus 1 squared, which is positive, since anything squared is positive. So I get negative over positive, which is negative, So in this interval here, I'm negative. That means also over here, I am negative as well. Okay, so that was between 1 and root 3. Next, I need to go to our point negative 1/2. So f prime of negative 1/2 is equal to 10 times negative 1/2 squared. That's positive. 1/2 squared minus 3, that's negative. So I have a negative on the top. Over 1.5 squared minus 1 squared. Well, obviously anything squared is positive. So I get negative over positive, which is negative. Negative here, and because of symmetry, I am negative there as well. Woo! So I am increasing from negative infinity to negative square root of 3. Let me write that down. So increasing negative infinity to negative square root of 3, and also positive square root of 3 to infinity. And I'm decreasing from negative square root of 3 to positive square root of 3, with some possible stuff going on there, but I am decreasing on that interval. Okay, next I need to do the same thing for f double prime. So I have a number line here for f double prime to find my inflection points. So my possible inflection points were plus or minus 1 and 0. And I need to pick one from each of these intervals. So for concavity, I cannot use symmetry, so I have to do every interval here. But for increasing, decreasing, I am allowed to use symmetry. So for f double prime here, I'm going to choose the points 2, 1/2, negative 1/2, and negative 2. All right, you guys ready? F double prime of negative 2 is equal to 20 times negative 2 squared plus 3. So negative 2 squared plus 3 is positive. So on the top here I have a negative number, and then on the bottom I have negative 2 squared minus 1, which is positive. So I have negative over positive, which is negative. So I'm negative on this interval. F double prime of negative 1/2 is 20 times negative 1/2, that's negative. Negative 1/2 squared plus 3, that's positive. So I have negative times positive, which is negative, over negative 1/2 squared minus 1 cubed, which is negative. So I have negative over negative, which is positive. So I am concave up there. Okay, I need to next find f double prime of 1/2. This is 20 times 1/2 times 1/2 squared plus 3. All of that is positive, over 1/2 squared minus 1 cubed. That's negative. I have positive over negative, so that is negative. And finally, f double prime of 2 is 20 times 2 times 2 squared plus 3 is 7. That's positive, over 2 squared minus 1 cubed. That's positive. So I have positive over positive, which is positive. Whew. Okay, so what this tells me is that I'm concave down from negative infinity to negative 1 and 0 to 1. Negative infinity to negative 1 and 0 to 1. And I'm concave up on negative 1 to 0 and 1 to infinity. I have run out of room, haven't I? You probably have too. So let me see, can I add a page? No, I can't. Okay, that's fine. So I'm just going to erase, I'm going to erase this right here. Hopefully you guys have some more paper on you. While I'm erasing, let me tell you a math joke. I've already told people in my Zoom session this joke, well, some of them. But why was the mathematician late for work? Because she took the wrong bus. Get it? Like the wrong bus. Oh, I literally have a whole book of math jokes. One year my mom gave it to me as a gift. It is literally a math joke book. It's my favorite. Okay, so we just finished step number 5. So let's go on to step number 6, which is finding the local maxes and local mins. So I have a couple local maxes and a couple local mins. Well, yeah. So because of the first derivative test, I see that here at the square root of -3, since I'm changing from increasing to decreasing, that means I have a local max here. And at positive square root of 3, I'm changing from decreasing to increasing. So that means I have a local min. All right. And I have, since my concavity changes at -1 and 0 and +1, I have those 3 inflection points. So I have a local max, we decided, at x equals negative square root of 3. And if I plug in a negative square root of 3 into my original function f, not this one, but the other one, I get -1. And I have a local min at x equals positive square root of 3. If I plug that into our original function, I get y equals +1. And I have inflection points, we decided, since my concavity changes everywhere, at x equals 0, -1, and +1. Those are my local maxes and local mins. What about asymptotes? That's next. So clearly, since I have a rational function here, I have vertical asymptotes wherever my denominator is equal to 0. And we decided that my denominator is equal to 0 at -1 and +1. Whoops. I don't know what I just did. Okay, so I have vertical asymptotes at x equals positive and -1. What about horizontal asymptotes? I need to determine my end behavior. If I look at the leading term on the top, it's x cubed. If I look at the leading term on the bottom, it's x squared. If I simplify this, I get x. So my end behavior looks like the function x, like that. So I have no horizontal asymptotes. Finally, I need to find my intercepts. To find my intercepts, I set my function equal to 0 and plug in 0. So if I take f of 0, I get 10 times 0 cubed, 0 squared minus 1. That's 0 over -1, which is just 0. So I have the point 0, 0. That is, so if I plug in x equals 0, that is my x-intercept, and in this case, it's our y-intercept as well. If I were to set this function equal to 0, if I get 10x cubed over x squared minus 1, if I set this equal to 0 to find my y-intercept, then I would get 10x cubed equals 0, which means that x equals 0. So just this guy for my intercepts. Okay, we are finally ready to graph this function. Are you excited? I know I am. So kind of like we did last time, let's first graph some points on our graph. So I have one intercept here at the point 0, 0. I have a local max at negative square root of 3, negative 1. And a local min at positive square root of 3, positive 1. What about asymptotes? Well, I do have two of them, two vertical asymptotes at negative 1 and positive 1. So this is x equals 1 and x equals negative 1. Those are my two vertical asymptotes. And then let's draw in my end behavior as well. So my end behavior looks like our function x, so I know that I will have an arrow this way and an arrow this way. But from here, it gets a little bit tricky. So now we have to go on to and look at increasing and decreasing. So we decided that I am increasing from negative infinity to negative square root of 3. So I'm increasing from negative infinity to negative square root of 3. And then I'm decreasing from negative square root of 3 to positive square root of 3. Well, clearly I have an asymptote here, so I can't cross over that. So I'm going to look like this, since I'm decreasing there. What about from x equals negative 1 to x equals positive 1? What is going on there? Well, I know that I'm decreasing, right? What about concavity? I think that can help us out. So I am concave from negative 1 to 0. I'm concave up. So I will look like half of a right side up U. So I will look something like this, right side up U. And then from 0 to 1, I'm concave down. So something like this. I am decreasing that entire way. So that's what the inside there will look like, going through my intercept there. I am still decreasing from negative 1 to negative root 3, so I will have to do something like this. And then I'm increasing from negative 3 to infinity. So this is what my function looks like. It is symmetric about the origin. If you flipped this function over the y and then the x-axis or vice versa, you would get this same function. Yeah, so this is a lot of details here, a lot of information. I am sure that you might have questions, so please come to the Zoom sessions if you do have questions, or post on the discussion board, and I would be happy to answer them there. But I hope you had fun. I know I did, and I will see you all next time. Have a good day.